3, 2, 1. Main engine start, 0, and liftoff.
It feels simultaneously like you want to dance and throw up at the same time.
Seeking clues to the planetary puzzle about life on Mars.
The calendar is clicking down to the day NASA will launch this rover to Mars.
Pit of your stomach feeling. It's this thing, this giant bomb that's taking off, and it could all be over at any moment.
We have first pair and second pair, both sets of SRBs have successfully jettisoned the vehicle.
The cameras on board this rover have been created by scientists at Arizona State University. Years of work are at stake.
Not all missions succeed. There have been failures on Mars. Half the missions sent to Mars have failed.
NASA's next Mars rover has a legacy that reaches back decades.
Use of an LSSM on the lunar
to groundbreaking work in Arizona's high country.
50 years ago, men first stepped off the Earth and onto the moon. But before those men stepped on the moon, they stepped here, on this loose volcanic rock, around these craters right here in northern Arizona. I'm Professor Vanessa Ruiz, and you're watching Catalyst.
This YouTube edition of Catalyst is brought to you by Arizona PBS and Arizona State University. Life has problems. Science turns them into questions that can lead to solutions and even innovations. This is Catalyst, shaping the future through science research at Arizona State University. Arizona is where men and machines first began to learn how we might move around on other worlds. We'll take you back to those beginnings and take you forward, up close, where NASA scientists are dreaming up new ways to explore the surfaces of the Moon and Mars. Crash landing, dust storm, dead batteries, or just plain stuck. Take your pick. Those are just a few of the things that will be on Jim Bell's mind in the months and years ahead.
I'm Jim Bell. I'm a professor here in the School of Earth and Space Exploration at ASU. And I am what they call the PI, or the principal investigator of the Mastcam-Z imaging system for NASA's 2020 Mars rover.
When we send landers or rovers to a place like Mars, it's very tricky to pick just the right spot to land. These craters, this loose, crunchy volcanic soil in this crater field near Flagstaff is full of the dangers and challenges a rover can face on a place like Mars. Even if a rover doesn't get stuck, there's only so far a rover can go. So just like when we go somewhere new here on Earth, the most important thing a rover can have is a camera.
It's no mistake that when we have rovers on Mars, they put the cameras at about eye level for humans so that we get a human perspective of being on the surface of Mars.
So what the mast does for us is it gives us a high platform, a couple of meters above the surface, and it lets us, spin those cameras all the way around 180 degrees, plus straight up or straight down.
Bell is part of the School of Earth and Space Exploration at Arizona State University, and he is leading the team that has put Mastcam-Z onto the Mars 2020 rover.
The mast is a structure on the deck of the rover. When launched, it's lying down on the deck. Everything's kind of folded up because you want to try to fit everything in this small capsule to get to Mars. But then after landing, the mast pops up off the deck, and it has a head on it, basically. And that head has 3 different sets of instruments. At the very top is a telescope, looks like the hat of the rover. And that's a telescope that the laser instrument uses to zap laser beams at rocks and vaporize them and get their chemical composition. Just below that, there's 2 camera systems on the outside. There's nav cams, navigation cameras, very wide angle, just for driving and arm placement decisions. And then the Mastcam-Z, which are inside, under the hat and inside of the nav cams, two cameras, and you can just see the square fronts of them, the square front lens elements. So the idea is to try to use the the capabilities of these science cameras to allow the rover to go farther, go faster, go into terrains that they might otherwise not want to go into. And we also wanted it to be able to support rover operations like driving. So we want to be able to take pictures at the right resolution so we could see things that are comparable to the size of the wheels on the rover so that we know about obstacles. Or see smaller features close in that the arm could get put down onto. Finally, we had to think about the kinds of science that we wanted to do and the fact that we didn't want to just send a copy of the same cameras that went to Mars before. We're always trying to make it better. How can we improve the cameras without scaring NASA? And the answer was use the same detector, fit it in the same volume, but give it zoom lens capability. Because the cameras on Curiosity, one is like a wide angle and the other was like telescopic. So it's kind of this myopic, weird vision between the two rover eyes. And it works great and they take great pictures, but it's very hard to do stereo because they don't match the resolution. So we wanted to instead take one camera system, a pair of cameras that could go from wide angle, stereo together, all the way to telescopic, stereo together. And so we can build these beautiful 3D views of the landscape. So we pitched that to NASA saying, hey, we'll use that 3D to help with drive decisions, to help with arm placement decisions, and to help with the science decisions about, what is this landscape like, what are the geologic processes, what's the context, and all that. And happily for the team, NASA really liked that idea and they picked our proposal, and starting about 5 years ago, we started designing and building the cameras. By modern digital imaging standards, these are not high-resolution cameras. They're 2 megapixel cameras. That seems like, wow, it's NASA, you should be sending 20 megapixel cameras. And the problem is that no one has yet built 10 or 20 megapixel cameras that can survive the violence of the shaking and shocks of launch and the extreme temperature ranges of being in deep space, and then the violent process of landing on Mars with retro rockets and hitting the surface, and then the huge temperature ranges down to minus 200 up to plus 30 every day. Your iPhone would crack, shatter, its sensor wouldn't work right. The sort of cutting edge technology, at least for Mars missions, that's where we're at. The 2 megapixels is cutting edge for surviving that kind of environment, for being beefed up and making sure it works.
Mars has a mystery for scientists that's also an enemy for cameras: dust. Seems strange, but yes, Mars even has dust devils.
Dust is complicated because it's everywhere on Mars. It gets into everything. It's going to be a huge issue for astronauts when they eventually go there. Imagine being in your kitchen and take a bag of flour and just throw the bag of flour around your kitchen and then clean it up. You'd never clean it up. You'd be finding flour in your kitchen for years and years and years, get into every little corner, every nook and cranny. And dust on Mars is the same way. It's smoke-sized particles, super fine. We don't really know what causes it. It's probably ground down from billions of years of erosion, but it could also be related to chemical alteration and weathering of the surface. So intrinsically, we want to get to know what it's like and really understand it, because it's everywhere and it's going to be a factor in not only for our camera lenses if they get dusty, but other components of the rover, seals and arm joints and wheels, and eventually human spacesuits and habitats and all that. We'll have to deal with it. So we don't have a way to clean the front window. There's not a front lens, there's a front window on the cameras. But we have kind of a baffle that will protect us from direct dust falling in. And when we're not using the cameras, we'll point that mask down so that dust doesn't fall on them. And then our experience from previous rover missions is that the lenses do get dusty, the front windows do get dusty, and then the wind blows and clears them off.
The Mars 2020 rover is going to visit a place called the Jezero crater.
After Jezero crater formed billions of years ago, water filled it to form a deep lake, about the same size as Lake Tahoe.
We're going to an ancient delta.
The canyon cutting through the crater rim was carved by a river. As the water entered the lake, it slowed and dropped the sand and mud it was carrying to form the fan-shaped delta. The white line is a path the rover might follow in its first 2 years.
We know on the Earth that the ends of that fan-shaped delta deposit, the fingers, if you will, are places where we see these beautiful layered rocks and these layers of sandstones and mudstones that are intrinsically just beautiful from a landscape perspective and likely to be so on Mars as well. But there also are the places where any past evidence of habitability might be preserved there. So we're not going to land on it because it's pretty rough, but we'll land near it and we'll see it off in the distance, and then it's going to be kind of a fun and exciting sprint in the early part of 2021 to get close to those fingers and get some pictures and chemical data and mineral data and maybe core some samples to eventually bring back to the Earth that material. I'm really looking forward to getting close to that delta and seeing what it looks like up close.
NASA, Bell, and his team have a lot riding on Mastcam-Z. From the Mars 2020 rover, it will beam back pictures from the surface that scientists will study for decades to come. It's due to launch in the summer of 2020. While Bell looks forward to all that, we've asked him to look back at some of the films that NASA made back in the 1960s.
The test subject proceeds from one point to another on his pre-planned traverse, stopping at stations which reveal promising features. All items necessary for exploration are carried on a tool carrier. The test subject proceeds from one point to another on his pre-planned traverse, stopping at stations which reveal promising features.
These stories were shot around Flagstaff, as scientists tried to work out how we would land, walk, photograph, and explore the moon.
At this geologically complex site, test subjects applied techniques and tools developed by the Center of Astrogeology to the task of exploration, much as it will be done on the first series of lunar landings.
So many of us wish that we could be there in a spacesuit and do those things and do the experiments and take the pictures and all that kind of stuff. And the technology has advanced dramatically from what was available in the 60s. It's all digital now instead of analog. But we can't go yet. And the best we can do is send avatars, robotic avatars, that have the cameras and the stereo systems and the sampling arm and all the tools that you kind of saw that astronaut carrying around. And we try to do the kinds of things we would imagine that we would do as geologists, as field geologists out there, through these very capable machines. Of course, it's slower. It's super, super slow motion field geology. They can work for a few hours every day, just given the power that's available to them and the temperatures that they have to go through and the environmental conditions.
Examples of this kind of information are walking speeds and time factors in various geologic exploration tasks. Mounted on the subject's surveying staff during part of the traverses is a Vidicon television camera simulating equipment being designed for post-early Apollo missions. This camera is used to transmit images of close detail to the CDRA. During a lunar mission, such images could be recorded, allowing much greater traverse coverage than possible with a photographic camera alone.
In many ways, a lot of us feel like we're like that subject in the field in his spacesuit, walking around, roving around, using mobility through robotics to get access to different kinds of geologic materials and different places.
Near Flagstaff, Arizona, are fields of volcanic cinders, the result of eruptions about the year 1065. The cinders provide an excellent material to recreate the lunar surface, and the geologic structure will offer training in mapping and sampling for astronauts.
So this is the area that they created for the Apollo astronauts.
What was it about this particular location, Laszlo, that made them choose it, to use it as a training spot?
There are a couple reasons why they liked this region. Overall, northern Arizona has a whole bunch of great geology that has the same kind of processes as we see on the moon. Volcanism and meteor craters impact But this particular spot for making a crater field, it's because we're walking on a bunch of volcanic cinders. And this is material that's easy to move, easy to blow holes into. And nobody really cares too much about using it for anything else. It's not great for farming or building houses on.
Placing explosives in holes at the right location and blowing them in the right order to match the age sequence is not all that is required to recreate a portion of the moon's surface.
So this is a very nice example of one of the craters they made over 50 years ago now. And what they did was they brought a backhoe in here, they dug a hole, they put a series of explosives in here, and then detonated it. And they were able to calculate how much explosive to generate a crater of a specific size. And if you look at the entire field of craters, it's actually reproducing a section of the moon. So it's not just making random holes in the ground. They're actually trying to make the right size holes in the right pattern on the ground to simulate a real part of the moon.
3, 2, 1, fire!
And so that's exactly what NASA did. Up here near Flagstaff's San Francisco Peaks, back in the 1960s, they made craters with dynamite.
And by doing the explosives, well, that's not how it actually happened on the moon. On the moon, you have something bashing onto the surface and that blows it up. The result is similar, that you have rock being blown up, falling back down, and quite often it's overturned to where you have the actual older rocks on the top, younger ones on the bottom. So they wanted to be able to mimic that as close as possible so the astronauts could, look at those layers of rock and understand what's called superposition, what's older and what's younger.
This is the orbiter photograph of the lunar surface. And this is an aerial photograph of the new crater field.
So here we are, Laszlo. We're in the center of one of the craters, and you were telling me that what they actually tried to do was recreate a specific surface of the moon right here in this patch of land near Flagstaff.
Right, so this corresponds to a real crater on the moon. It's got the right diameter and the depth, and the other craters around have the same size and the same distance away. So it's really trying to reproduce a patch on the moon. Oh, they brought in rocks from all around the country to put together a story here for the astronauts to try to figure out. So it's almost like their final exam here to make sure they could recognize rocks that were different, describe them well enough that people on Earth could tell what they were, and see if they themselves, while they're walking around the moon, could put together a story of what happened.
This became the practice field for astronauts like Neil Armstrong, who would go on to be the first man on the moon.
Rover will not go to the moon, but it is a valuable tool for training our astronauts to explore the lunar surface more effectively.
For the later Apollo missions, Flagstaff's cinder craters again became a kind of proving ground. This time to test drive the Dune buggies astronauts rode in Apollo 15, 16, and 17. NASA called them LRVs, Lunar Roving Vehicles. Those LRVs and other developments brought us to the unmanned robotic rovers, like the Mars rovers, and the one that will soon carry Jim Bell's Mastcam Z to Mars.
What we're doing is very, very similar to what they envisioned astronauts doing, and of course what many of the astronauts did on the moon in the 60s, late 60s and early 70s.
Lava and volcanoes are a big part of this landscape around Flagstaff. The San Francisco Peaks are volcanoes. You don't see it on the surface, but underground, this area is riddled with holes, what scientists call lava tubes. A half-hour drive west of the Flagstaff cinder craters, NASA scientists are working on a new rover for a possible future moon mission. A mission to the moon's lava tubes.
It's called Moon Diver, and so they want to go into these lava tubes, and so I think it's really exciting because we don't yet know the effects, we don't fully understand the effects of space weathering. We're only able to access the top tens of centimeters if you get to go down into these tubes, you can really see the unaltered lunar materials.
So Arizona offers this rich and diverse terrains that we can field test our robotic systems.
I'm Laura Kerber, and I'm a research scientist at the Jet Propulsion Laboratory. And we're out here in Arizona testing our rover called Axel in preparation for this mission concept that we have that we're proposing to NASA, which is called Moondiver.
Okay, now go forward. Moondiver is this exciting mission to go to explore one of the lunar pits.
We found these deep caverns on the moon, and they go down into the moon and they have some kind of lava tubes perhaps underneath, and we wanted to take a look at the layers in the side of the pits on the way down into the tube.
By going down that pit wall, you can explore the history of the moon by looking and examining the rocks as you go down. The reason why it's called Axel because it looks like an axle. It's a tethered rover, a little bit like a Segway, but with a tether running through it, and it's capable of driving on the surface of the moon, rappelling down the walls, and taking measurements. So here you can see an area where the rover deployed its grinding tool. It ground this 2 by 3 centimeter area, and that prepares a flat area that's pristine for the other instruments. And as we take the measurements, we can study the fine composition of these rocks, and that informs us about the history of the basaltic layers on the moon.
We have this rover that's a rappelling rover. It attaches at the top to our lander, then it rappels down into the hole. It's deployed! Oh my God!
These are the most recent prototypes that we have developed. These are basically, as you can see, giant wheels. So as we want to move forward, we just turn these wheels, and what happens then is it pushes this back part of the rover into the ground. So you may be used to like a 4-wheel rover or 3-wheel. These are 2-wheeled rovers. You can see there are 2 different versions here. We have the Mars adapted axle here, which is one that we're targeting for a long duration autonomous mission on Mars. As you can see, it has a different set of hardware than this other one here. That's because this one is designed for spooling the tether in and managing it internally so that it can be safe on those long duration missions.
Okay, we're heading down now.
What we were looking for in a landscape is we wanted a relevant environment, which means that it has to have the same geometry as the environment on the moon and the same chemistry so that we can test our instruments.
We took this one out just recently into Arizona, into a pit crater, and we did kind of an analog mission into a relevant geography. So we had a pit crater there in Arizona. We drove as we would in the lunar mission, and then we rappelled into the crater.
So this particular hole is a basalt layer. It's actually a sinkhole, so it collapsed underneath because there's limestone underneath. On the moon, it collapsed because there's a tube underneath. But the similarity is that they both have this nice, big, thick lava flow that we can look at with our instruments.
This one, by comparison, is the lunar adapted axle. So this one has a much simpler internal design, and it has a very different instrument suite. So you see these large aperture cameras here.
This rover is a really innovative rover. It's a lot different from the ones you see like Curiosity and Opportunity that are on Mars. These are 6-wheeled rovers that go around on the surface. This is actually only 2 wheels, and that's why we call it axle. It's like a big truck axle. And then the wheels have inside the wheel wells all of the instruments. And so it has the 2 wheels and it has a tether, and it gets communications and power through that tether.
When you're driving down these steep slopes in this complicated terrain, you have to watch what the tether's doing. The tether changes to one side of you. It limits how far you can drive. And also you have to watch what the tether's doing. It may snag on the terrain in certain points.
The instruments come out of the wheels and they measure everything. It's just a really simple system. And we love the simplicity of it because there's not a lot of ways it can break on the moon.
The things that we'll be able to do with this mission is actually go to a place where we couldn't have gone with other rovers, examine a very exciting new exposed bedrock on the moon, and from that we can understand the history of the volcanic activity on the moon. So it gives us a peer into the interior. We're probing in the moon and we're looking at its interior. The Mars rovers are fantastic machines that are extremely capable and explore the red planet over almost 2 decades. Now, one of the things, these rovers are designed to go over rugged terrain, rocky terrain, but largely terrain that is either flat or within about 30 degrees, upslope or downslope. When we look at these lunar pits, The stratigraphy and the topography of these is such that they are pretty much vertical walls in the, in the most extreme, and sometimes they could be overhung. So what we needed to do is design a simple robotic system that is capable of going over much steeper walls. We have systems that can do that. We have things like a yo-yo, which can go up and down, that does not require any wall. And so we designed this robotic system to be like a motorized yo-yo, where we actually put wheels on it, we put a spool, we put a boom, and now we have a capable system that operates like a yo-yo, where it goes up and down on a tether, and hence can explore very extreme and very steep terrain.
We'll get a better sense for what these lavas really were doing when they were emplaced. They're certainly very interesting, and it's probably just a matter of time before we wind up there.
Thank you for watching Catalyst. I'm Professor Vanessa Ruiz. And because science always has new questions to answer, we'll be back soon with more stories.
Catalyst is supported by Knowledge Enterprise Development at Arizona State University, advancing entrepreneurship, innovation, discovery, and knowledge for the public good.
Subscribe to this channel to see more episodes of Catalyst on YouTube.